Alright, that is the event ping that just went out. I'm just kind of waiting to see if root is going to ping directly or if they are just going to let the event handle it. Let's see here. To anybody who's watching this talk in video mode, you might want to skip ahead a few minutes. I'm not sure when it's actually going to start. Well, first of all, I gotta wait until there are actually people watching the stream. I'm not gonna present for 0 people. So let's just wait for some people to join. Alright, ping just went out. And now we wait. We already got 2 viewers. That's great. What's going on, chat? Somebody asks if you can use this talk and apply it to C++. I would say that you can. I'll be using the Pthread library, which is also available in C++. So, yeah, it should work. We got an admirer in the chat. That's great. No, I'm not going to be covering the C11 threads because not every compiler supports it, and Pthread is more ubiquitous. Will this multithreading be compatible with C99? Yes, but at the end I'll talk about atomics, and C99 doesn't have atomics, I believe. So only that part will not be compatible. Just gonna wait a little bit longer. Oh, I forgot to introduce myself. So you probably know me as Clue in the Discord server, but my real name is Michael Rudeveld. Yeah, somebody is noting in the chat that C11 threads and Pthreads are pretty similar. Yeah, they are. It's almost a copy and paste job, honestly. Dutch representative. Yes, indeed, I am from the Netherlands. I hope that my accent doesn't shine through too much, but I think it's inevitable. But hopefully you'll understand me. Alright, I've waited long enough. I'm going to start presenting. So, multithreading in C. Principles, techniques, and tools. So my name is Mike Rudeveld, and I'll be telling you a little bit about how to multi-thread in the C programming language. In this talk you'll learn some of the theory behind multithreading, its uses and its limits. Those are the principles. You'll learn how various multithreading ideas are applied and which kind of constructs you can use to achieve goals. Well, let's say you have two threads and they work together to achieve some sort of goal. How do you do that, right? So those are techniques. And lastly, perhaps most importantly, you will learn how to compile and debug your programs, which tends to get kind of a bad reputation. We have a lot of questions about how to get your program to compile, but I will show you it doesn't have to be hard. So I'll first explain what multithreading even is and what it's about, and then we will be faced with our first problem. Hello world. Yes, quite monumental. We'll also be seeing our first bug, and for that I'll be using the thread sanitizer to squash the bug. And I'm going to be talking a bit about race conditions, and we're going to be using so-called locks to solve them. But locks come with their own problems, such as deadlocks and resource starvation, which I'm going to be telling you all about. And lastly, conditions, which you can kind of think of as events. And well, lastly, a little bit about atomics and the volatile keywords and what they really mean, because volatile gets a lot of misuse, and I think it's time that the misuse stops. So what is multithreading? Well, multithreading is just when you have some code and you are running it from multiple threads. So usually when you have a program, there is one thread of execution, right? You do one thing after another. But when you multithread, you're doing things at the same time. There's two code paths or more, each for one thread. And a thread is just a lightweight process. And a process is just a running instance of a program. Now you hear a lot about concurrent and parallel, and they both mean at the same time. And multiprocessing, well, that's kind of the same concept, but you replace a thread with a process. But it's really the same concept. So allow me to just grab a terminal, and I will show you a little bit of an example. So we're going to be using the Linux Task Manager, HTOP. And I'll show you a bit about multithreading. Oh geez, the text is really big. So each green thing here is a thread, and each white thing here is a process. So for instance, you have this program called cronD. It's just a program, it doesn't have any threads. But here you have a program called Network Manager, and it has two little children threads. Now if you look through my system, as I scroll along here, you'll see tons of threads. Almost every program uses at least threads in some form or another. So threads are everywhere, and yeah, I just thought it was kind of neat to show you guys. So why would you use multithreading? Why do all these programs use threads? Well, first of all, you can model the real world using multithreading. So our world is asynchronous. Things happen at the same time and with no real defined order. It's kind of chaos out there. So what if you took that idea and put it into programming? You get multithreading. So it allows you to model the real world. For instance, you might want your program to wait for a certain event to happen. Or maybe you just want to do multiple things at once. Knowing about multithreading is also important because it allows you to squeeze the maximum performance out of processors with multiple cores. Most processors these days are multi-core, and yeah, so if you don't multi-thread all of those cores, they just kind of go to waste, which is a real shame. So here's a normal program. This is programming in series. Let's say you have a function called compute, and you have two numbers which you want to compute. So in the main function, there's first compute1, and then there's compute2. And well, after that is done, the program is done, it exits. And here's what that same program would look like in parallel. So here you have the main program, it starts, And what it does is, instead of a computation, it creates two threads, and each thread has one computation going. Take a bit of water. And what's important here to note is the join threads thingy. So the main program, the main process, has to wait for the computations to finish, and that is symbolized through joining. This is called the fork join model of concurrent programming. The reason why is, if you have a little bit of imagination, you can kind of imagine a pitchfork. Right, so main starts out as one long handle, and then at the point where it creates threads, it kind of turns into a pitchfork. And then after the threads are done, you join them back together. So that is the fork join model of concurrent programming. So you would say that it is twice as fast, right? If you do two computations at once, instead of waiting for one to complete and then waiting for the other, you're doing it at the same time. So it saves time. Well, Amdahl's law is here to ruin our day and give us nightmares, because it's not always that simple. Not every program can be parallelized easily. So let's look back at the previous slide here. What we're doing here is we are creating threads and we are joining threads. We're creating them and then waiting for them to finish. And those things are not parallel. We have to do that from the main process. So the only thing here parallel is the actual computation itself. So the simple program which I just showed is not 100% parallel. Probably more like 95%. So if we here look at the pink curve here, not sure if my mouse cursor is big enough, but the pink curve, that's 95% parallel. And you can see all the way at the top that you will only ever get a maximum speed up of 20 times faster. Which is kind of crazy, because if you look at the x-axis, oh, by the way, it's kind of labeled wrong. I stole this graph from Wikipedia. It's supposed to say number of threads, but it doesn't really matter. Anyway, if you throw 65,000 threads at the problem, it'll only get 20 times faster. And most programs are not 95% parallelizable. Most programs are probably, well, even 50% would be a pretty great number. But if we look at the bottom left, we will see that if we have two processors or two threads, and then we can expect about a 2 times speed up, right? And if we have 4 computations which we would run in parallel, we wouldn't get a 4 times speed up. We'd get a little bit less, about 3.8. And that's kind of how it scales. So those are the limits of multithreading, and this is a mathematical thing. You can't really escape it. Right. So let's jump into our first example here. We're going to be using the Pthread library, which stands for POSIX thread, and POSIX is an operating system standard, and so it's widely available. And we're going to be using the Pthread option here in our compiler to compile it, and I'll even introduce a subtle bug, and we'll debug it using a thread sanitizer. So we are going to create a document, demo1.c, and well, first of all, we start off with increasing the font size. There we go. Not sure if this is readable. I think this is big enough. We start with including standard io.h because we are going to print hello world. Secondly, we're going to be including pthread.h because we're going to be using threads. Then we get our main function as usual, and you would say hello world, except we're going to do this multi-threaded. So if you think about it, main is kind of the entry point of our program. It's where our process starts. Likewise, a thread also needs an entry point. So let's call it thread fun. And in pthreads, a thread entry point has to return a void pointer, and it has to take in a void pointer argument. Now we're not going to be using that argument, so I'm going to cast it to void so that my editor doesn't yell at me. And we're going to say hello world from the thread, and then we're just going to return null, the null pointer. because I don't really have anything interesting to return. Alright, and then it's time for a function called Pthread create, which will create a thread. And the first argument that it expects is a little handle in which it will store some information that it needs to handle our thread, and it is stored in a pthread type. So let's call it thread. We don't really need to initialize it, and we'll pass in a pointer to our thread. And the second argument it expects is a bunch of attributes. You can give your thread attributes and that'll change its behavior slightly, but that's out of the scope for this talk. I'm not really interested in that, so I'll pass in null. And then it expects the actual function that we want to run, so I'll pass in thread fun. And lastly, the argument here can be passed in from here, but I don't really have anything to pass into it, so I'll just pass in null. Alright, and then we are going to open a terminal, and we're going to increase the font size again. Hold on. Well, alright, that works, I guess. Let's see, what kind of files do we have? We have demo1.c. Don't forget to save your file. We're going to do gcc pthread demo1.c. We're going to tell it to call the executable demo1. Alright, and now you can see that a little program has occurred called demo1. And we're just going to run it. And it says hello world 3 times. Well, that's kind of weird, isn't it? Because, well, I only called hello world once. So what happens here is a little mistake I made. We have to actually join our thread. And it also expects you to handle the return type, but I'm not returning anything, so I'm just gonna pass in null again. And we're gonna remove the hello world from our main function. And now I think you will all agree that we expect a single hello world to happen. And it works, a single hello world, and no more weird extra hello world bugs. What can happen if you don't join your thread is sometimes what happens is there's no output, right? Which is kind of weird because we are clearly creating our thread, but it's not really printing anything out, which is kind of weird. But it's not actually weird if you think about what's happening. Our main function here is starting up. It makes a little thread container. It then calls this function, and then it immediately exits. And our thread here never really has the chance to run and properly say hello world, and therefore you get no output. So we can debug that by adding in some debug information with the G switch, and we'll do fsanitize, oops, if I can type, fsanitize equals thread, and then we run demo1. Thread sanitizer will say that we have a thread leak. In other words, we forgot to wait for our thread. The thread is still ongoing and we already exited. And the first thing it mentions is kind of useless to us. It's some sort of internal function. But this one is quite useful. It says which file is affected, and if we look here at line 13, yes indeed, that is where we create our thread. And so Pthread is telling you, hey, at this line you create a thread, but you never join it. So then if we solve the bug and we compile it again, nothing happens, and we just get our normal hello world, and Thread Sanitizer shuts up because Thread Sanitizer is happy. Let's see if we got any questions in the chat. Is this recorded? Yeah, there will be a recording posted after the talk. Somebody asks, so some pthread functions take pthread t as a pointer and others take it as value. Yes, that's right. This is called a what do you call it? An output parameter. So because C only has a single return type, you have to pass in the object that you want to modify. So pthread create takes a pointer to thread because it modifies this variable itself, and therefore it needs a pointer. And actually pthread create has a return value which I'm completely ignoring. And you can test for it, and if it's not if it returns anything non-zero, that means an error has occurred when creating the thread, and you can use the this function perror to print out what exactly has gone wrong. Alright, so I'm gonna move back to the presentation here. Too many open windows. Oh, actually, there's not much point to creating a single thread, right? So let's have some fun. Let's make this an array of 8 threads, and let's wrap our creation in a for loop. We're gonna lift that in there, delete that, and since we are now accessing an array of threads, we also have to do that correctly, and we also have to join an array of threads. So why is it not auto-completing? Here we go. I'm gonna join, there we go, join thread number I, and let's see, we don't need thread send size for this. And what you'll now see is 8 hello worlds. So 8 hello worlds is because we are creating 8 threads, and they all say hello world, and then we wait for each thread to finish, and then we return. Whoops. So here's a little diagram of what just happened. Main starts, we have our create, and then you have 8 hellos. And keep in mind, all this time the main function is still running. And then you join your threads, you wait for all of them to finish, and then you exit. Can I explain Intel SMP? Oh man, SMP. So that's a different kind of thread. So some processors will advertise that they have hyper-threading or something like that. There's a difference between OS threads, and what I just showed you is an OS thread. But CPUs also have threads. A CPU has cores, and each core usually has 2 threads, and they're different things. And a thread on a CPU is basically a mini core which shares some common components, and a thread on the OS is basically like a lightweight running program. So that's the difference, and I am talking about OS threads. So let's talk a bit about race conditions. 2 threads are racing to read or write a value, and this has possible control flow implications. For instance, if you have some sort of some thread which is modifying a variable and some other thread which is reading that variable, well, it depends on the order, right? If the write happens before the read, then you might get a different result in the if statement. It might take a different path. So I'm going to show you right now. I'm going to make a new file. I'm going to call it demo2.c, and I'm going to copy and paste most of this code. Here we go. We're going to make a global variable here. We're going to say I don't know, int var equals 0, and in our thread function I'll do var equals 10, and in our main function I'll remove the loop. There's no need for that. Remove this loop and that one, and make this a single thread again. So let's see, and then I want to test the variable. So if it is bigger than 5, then we'll say bigger, and if it's not bigger than 5, we'll say smaller. So what do you expect to happen here, right? We are making our thread, and what happens is we set the variable to 10. So we create the thread, it sets the variable to 10, and then we test it, right? And 10 is always greater than 5, so we should see bigger. Well, let's see if that's actually the case. gc pthread demo2.c /o demo2, and we'll run that program, and it says smaller. So that's kind of weird. What gives? Well, this is called a race condition. Basically what's happening here is our main process is racing to read the variable, and our side thread here is racing to write to the variable. And one way we can solve this is by joining our thread. So what happens here is we create our thread, it sets variable to 10, and we wait for that thread to finish. And only after it has finished, we finally test the variable. So let's see if that works. And now it prints out the correct thing. So just for completeness, I'm going to reintroduce the bug, and I'm going to compile it with thread sanitizer. And we're going to run it again, just to see what that looks like. So here thread sanitizer has correctly identified the data race. It calls it a data race. Race condition data race. It's kind of a synonym, right? It means the same thing. And what it says here is read of size 4. So the size is an integer, it's 4 bytes. It's not really important. Here is the reading at line 18. And here is the writing at line 8, which checks out. So thread sanitizer tells us, okay, hey, you're doing something wrong here. It's not telling us how to fix it. We have to be creative enough to do that ourselves. So we can fix it again by waiting for the thread to finish first. Right? Alright. Back to the presentation. So in this case, we solved it by serializing our program again. We we synchronized our thread to the main process, and we kind of forced an order with that. And another solution could be locks. So if you think about well, let's say you're going to school or to some sort of restaurant, it likely has some restrooms, and usually a toilet is accompanied by a stall which has a lock on it. So think about why that lock is there. It is there so only one person at a time has access to the toilet, right? You don't want two people, you don't want to sit down on the toilet and then suddenly somebody else barges in. That's not really, well. So in multithreading, you have locks for much the same reason. And in this case, our variable, you could see it as the toilet. So let's solve this problem using logs. So we'll do pthread mutex t. Now a mutex is kind of a weird word. It's an acronym. It stands for mutual exclusion. Right? So only one at a time. And we'll call it var lock. And you need to give it an initializer here in all caps. That's just kind of an oddity. So in our thread fun, we will try to lock it. And you have to pass in the pointer to varlock because it will modify some of the internal state of the lock itself. And then after you've locked it and you've done your business, you can unlock it again. Right? And so now instead of waiting to join it, what we are going to do is we are going to acquire the lock first. Pthread mutex lock. For lock, there we go. And then hold on, actually this won't work. This is not really a good example. Here's a better example. Here's a more fun example anyway. What I'm going to do instead is inside of this function, I'm going to comment this out for a bit. And let's add 10,000 to our variable here. And let's create an array again. So I'm just going to copy that code real quick. There we go. So now we have 8 threads, and they're all going to be adding 10,000 to the variable here. And what you would expect to see is 8 times 10,000 is 80,000, right? So you would expect to see, if I just print out the value of our var here, make it look nice. There you go. You would expect to see var equals 8,000, right? So let's see if it actually works. And it's not even close. Not even close. It is 35,000 and some weird number. So what the hell is going on here? Well, var++ actually consists of multiple steps, right? So what happens in the register, in the CPU, what happens is first var is loaded into some CPU register, and then the register is added together with 1, and then the register value is written back to the variable. So this is kind of what happens inside of the CPU. Now, register is a deprecated keyword. It still exists, but it doesn't really work anymore. Yeah, see here, it's already complaining to me. Oh, register int. There we go. And we get kind of the same wacky result, right? We get like 35. Here we get an even lower number. So what we need to do here is we need to lock the number, and then we need to unlock it. We need to lock the stall, we need to do our business, and then once we are done, we can continue on our day. So let's see if it works now. And now we get the correct result, because now this is not an issue, right? So why do you need to, why can only one lock at a time do this? Why can't multiple threads, I mean, do this at once? Well, what happens, for instance, let's say var equals 0, right? And so thread number 1 loads the number 0 into a register. And at the same time, a second thread does exactly the same. So now there are two threads with running on 2 cores, and both have the internal number 0. And they both add 1, so both threads now contain the number 1. And then both at the same time, they write the variable back. And so thread number 1 writes var equals 1, and thread number 2 writes var equals 1. And so they have both incremented, but they're not, they're not really aware that they are interfering with each other's business. And so that is why you need the lock. You need to force only one thread at a time access to do this, and you do that with a mutual exclusion lock. Alright, so that was the example I just gave. We used locks and unlocks. And oh, I forgot to show what the thread sanitizer output for that looks like. So let's remove the locks again, and just really quickly go up, go up, go up. Right, and now thread sanitizer complains again about the data race. It says that we are writing here at line 12. Oops, let's remove that. Let's compile it again, run it again. So we are reading at line 12, so we're reading it into a register, and then we are writing it back a few lines later, and that's a data race, right? I just explained that two threads can do this at the same time, and they end up with the same internal register value, and they write back the same value at the same time. So that's a counter. What's good to know here is that a piece of code surrounded by a lock, like that for loop which I just showed you, that's called a critical section, and only one thread at a time enters the critical section. Now some libraries have dedicated functions for this, but in Pthreads I'm not actually sure, but I'm just doing it the manual way. And a thread save function, I guess I should mention those. A thread save function is when a function can safely be accessed from multiple threads. So let's say that this is our thread right here, and we're calling some sort of function. Let's do the pow function. Pow raises a number to a power, so let's raise 2 to the 4th power. Alright, and we'll do float result equals 2 to the 4th. Well, this is a thread save function. You can run this from multiple threads, no problems at all, right? But some functions require that only one thread at a time. Some functions require that only one thread at a time has access to it, right? Because maybe they are internally relying on something like a global variable. And so what happens in those cases is you need to, what I like to do is I like to wrap it So let's suppose for a second that pow is thread unsafe. It isn't, but let's suppose it is. We'll do a float b, and what we'll do here is we'll just call the normal pow function, but we are going to lock it first. So you'll have your pthread mutex lock, your pthread mutex unlock, and then you have safe pow lock. Hold on, pthread mutex t safe pow lock. So this is what a thread safe function looks like. If you have a thread unsafe function, we'll store our result, and then once we have unlocked the lock, we will return our result. It's important that you first unlock it and then return it. So this is how you make a thread safe function. Now again, pow is, as far as I know, perfectly thread safe, but it's just an example. You also have TryLock and WeightLock, and well, imagine going back to the bathroom example. Imagine you are going to the bathroom and you see that the stall is locked, right? What do? Well, usually there are multiple stalls, so you go right to the next one. But suppose there's only one bathroom stall. What do? Well, you'll probably wait a bit. But if the person inside of the toilet is taking way too long, you'll probably give up and just look elsewhere in the building for another toilet. So that is what WeightLock does. WeightLock allows you to specify a time, and if it can't lock the lock within that time, it'll just move on. And the way you use that correctly or smartly or whateverly is, let's use this function again. So we are going to change this into a TryLock, yep, or no, a WeightLock. No, let's do a TryLock. A TryLock is kind of like a WeightLock, except it has zero patience. It immediately gives up if it is already locked. And what we will do here is we'll put this in an if statement. And we will say we did not acquire the lock, and if it succeeded, we'll say we acquired the lock. So this looks kind of weird, right? You would expect these two to be swapped, but the thing is, if it successfully locks the lock, what happens is it returns 0. So this condition will get triggered. If it does not get the lock, it will return non-zero, and so this condition will get triggered. And what we're going to do here is we're going to go back to one thread, back to one thread, and what we're going to do is we're going to lock the lock before the thread has a function. The thread has a chance to lock. So let's lock it and let's unlock it. So would you agree with me here that since we are locking variable lock, and thread function here tries to lock variable lock, this will never work because it's already locked, right? It is locked before this function is even born. This thread, before this thread is born, it is already locked. It will never acquire the lock. And we can remove that. So let's compile that. Oh, I'm using the pow function, which requires math. Let's just comment that out, it's not really important. And let's run demo 2. And thread sanitizer complains. Hold on. Did I do everything correctly? Oh, right. I'm unlocking a lock here, but it's not actually sure that I locked it, right? I only try to lock it, but sometimes it fails to lock. So we need to make sure that we only unlock it if we actually acquired it. So now thread sanitizer should shut up. Oh, I forgot to rename it. There we go. And it will say we did not acquire the lock because we already acquired it here. Now if the main thread does not acquire the lock, then our side thread here will be free to acquire the lock for itself. So if we recompile it, this time it does acquire the lock. So that's how TryLock works, which can be really useful in some cases. Alright, deadlocks. This one is fun. So when you use multiple locks, right now we've only used one lock, but sometimes you'll get a situation where you have 2 locks or 3 locks or maybe even more. And what can happen is if there are 2 threads that kind of lock the same kind of resource and they kind of depend on the resource being unlocked, if you're not careful about the order in which you lock your locks, then you can get a deadlock. So here's a classic example. Here's a kidnapping, right? So a thief kidnaps a woman, and the thief says, I'll let her go when I have my ransom money. Well, the husband, he's not dumb, so he'll say, okay, well, I'll pay ransom when I get her back. And this is a deadlock. Why? Well, because the thief depends on the husband giving money, but the husband giving money depends on the thief giving back the wife. And until either one of them steps forth and does it, it will never get resolved. So this is a classic example of a deadlock. So I'll do a quick demo of this, and I don't feel like typing it out again, so I prepared a couple of examples here. So here's a deadlock, right? So we're going to symbolize our woman with a lock, and our money is another mutex lock. And here's the husband thread, and the husband has the money, but he wants to get the woman. And the thief has the woman, but the thief wants to get the money. So notice that these are in opposite order, right? Husband first locks the money and then the woman, and the thief first locks the woman and then the money. Now I have wrapped this in an infinite loop so that we get a better chance at seeing a deadlock, because as I have written the code here, there can exist a deadlock, but it doesn't have to happen, right? There's a little bit of chance involved. So here we'll start the kidnapping simulation. We'll create a thread for the thief, and well, actually, here's a serious bug. Those should be separate threads. And same here. So we'll start the thief, which locks the woman and then the money, and we'll start the husband, which locks the woman and then the money. So hold on. Let me just get into the correct folder. Demos. Alright. And we're going to compile our deadlock example. And we're going to call it deadlock. And then we're going to run deadlock. Alright, you guys ready? And so what happens is you see a whole bunch of thief has both resources, and then it suddenly stops, right? This is an infinite loop, so it's continuously printing, and then it suddenly stops. So what happens here? Well, if we consult the code again, you'll see here it's continuously, apparently, running this loop, which is probably because we started the thief first. And now the husband never really gets a chance to lock it, because the thief locks it, and then he unlocks it, and this happens so quickly that the husband just doesn't really get a turn. But when the husband finally does get a turn, you'll get a deadlock. You'll never see husband has both resources. Instead, you'll get a deadlock because the husband never progresses past this point. Why? Well, the thief already locks the woman, so husband cannot lock it. And thief cannot lock the money because husband already has it. And so they get stuck, right? So let's see what this looks like from the eyes of the thread sanitizer. And it should work. Alright. So immediately here we get a bunch of colorful text here. And what it says is warning, lock order inversion, potential deadlock. It says potential deadlock because as we saw, it doesn't have to happen immediately, right? Thief prints a whole bunch of times before the final deadlock happens. So that's why it's a potential deadlock, and eventually it does happen. So it throw some memory addresses at us. It's not really that interesting. Here's what we're interested in. It says here's a mutex 1 and here's another mutex, and in this file on line 26, so that's right here, we're locking, or we're trying to lock money. And then in this file on this line, so that's line 13, we're trying to do the opposite, right? And here it says 42. What is at line 42? Oh, here we are creating our functions. So thread sanitizer here gives us the lines where we create the threads responsible, but it also tells us the lines responsible for the wrong locking order. So how do you solve it? Well, I already have it here. The solution is an agreed upon lock and unlock order. So if we swap these two around, and we swap this one around, now you'll see that both the husband and the thief lock the woman first, then the money, then unlock the money, then unlock the woman. One principle is that you have some sort of locking order. In this case, the order is woman, then money. And the unlocking order always has to be the opposite, right? And both thread functions, both threads, they are now in agreement. They agreed on a locking order. So let's save our file, and we're going to quit our program, and we're going to try it again. And now you can see that they're alternating, right? Every now and then the thief has a streak, and every now and then the husband has a streak. What's interesting to note here is that they have streaks at all, right? Why does this happen? Well, there is some overhead in trying to lock a lock, and whenever you don't get the lock, it waits, and sometimes it waits for too long. And so let's say that thief is waiting for a woman to unlock, right? Thief likes to run, and he's waiting for the woman to unlock. But the husband has already locked the woman, and the husband unlocks the woman. So then you'd say, alright, now the thief can swoop in. Well, no, actually, because the thief is waiting just a little bit longer, right? There is some granularity involved here, and the granularity is too large. Sometimes it skips, it doesn't immediately get its turn. So that's why you see these long alternations. And this is only made worse by the fact that, in fact, the only thing we're doing is locking and unlocking. If we had some extra computations going on in these threads, you would see the effect less pronounced. So that's a demo of a deadlock. And usually a symptom of a deadlock is that your program gets stuck, right? It printed that the thief... Hold on, let me see if I can get that output back. Oh man, that's really long. Let's see here. Right, so here's the old output where we still had the deadlock issue, and it just printed and printed and printed the same thing over and over again. So when that happens, and the program finally hangs, and it gets stuck, no more progression, that's a symptom of a deadlock. And a deadlock requires two threads to depend on each other. In this case, the thief depends on an action of the husband, and the husband depends on an action of the thief, and one of them can complete, and therefore none of them can complete, and that is a deadlock. So the moral of the story is they should have just agreed on an order. So let's look at resource starvation. Now what's interesting here is that this already is kind of an example of resource starvation. Thief here, in this old example, is the only one that gets the resource, and the husband never really runs. So the husband, as we say it, is starved of resources. But there's a more simple example. So let's say you have 3 threads running a while loop, and there are 2 locks, right? And thread A uses lock 1, and thread B uses lock 2, but thread C uses both locks. So make a prediction in your head. If you wait 5 seconds, you just let the program run. If you wait 5 seconds, how many times will C complete the loop? How many times will A complete the loop? How many times will B complete the loop, right? And the answers might shock you. So here I have programmed it. We're using this function here for sleep. If you are on Windows, you are likely going to be using the Windows API for it. And here we have our lock 1, and here we have our lock 2. And here we have 3 counters, and these just count how many times thread A runs. So this is how many times thread A runs. This is how many times thread B runs. This is how many times thread C, etc. And here we have a little global variable, which is a bit dirty, but oh well. And we're going to be using this variable to kind of synchronize our threads, to tell them, okay, you can stop running now, right? Because we only want to run this simulation for 5 seconds. Now, I added some extra locks here, which don't really do anything. They're not really connected to anything, but they are to kind of even out the benchmark, right? So here in thread A, we are locking lock 1, and we are unlocking lock 1. And we have also lock 11, which is a private lock. Nobody else touches lock 11, but I just added these so that every function is locking and unlocking two locks. And here in thread B, we are locking lock 2, and we are unlocking lock 2. And in thread C, we are locking lock 1 and lock 2, and we're unlocking both of them again. And again, these 11 and these 22, those are just, you can ignore them pretty much. And here we have 3 thread handles. We are creating thread A, B, and C, storing them in them. Let's run this for, I guess 10 seconds is long enough too. And we're going to, after the 10 seconds elapsed, we are going to say running equals 0. Now, I have the variable running here surrounded by a lock. The reason I have that is to prevent a data race, right? Because our main process here is writing 0 to the variable running, but the threads here are reading the variable running. So you want that to be synchronized with a lock, otherwise you get a data race. And after that, we just join them, right? They have stopped their while loops, and they are ready to join. And then we kind of calculate the total amounts that each thread gets to run. So let's scroll all the way back to the bottom here. Okay. And this one called starvation. And let's compile it, and let's forgot to give the name. And let's run the program starve. And now we're going to wait 10 seconds. So have you got your predictions in yet? So thread A, thread B, thread C. Which one is going to run most of the time? So what might surprise you here is that thread B runs about 70% of the time, and thread A only runs about 7% of the time, and thread C runs 21% of the time. So why is that surprising? Well, if you're like me, then you would have expected thread C to run about a third of the time, thread A about a third of the time, and thread B about a third of the time. Except thread C locks both resources, so it has to wait a bit longer, right? It has to wait for 2 resources instead of just 1 to become available. So you would say that C kind of runs maybe 20% of the time, and thread A and B, they both run the other 80%. But as we can see here, that's not true at all. Thread B ends up running by and far the largest amount of the time. So that's kind of weird. So let's see what happens in B. Well, nothing all that special. We're just we're getting the lock 2, and in thread A we're getting the lock 1. But what's really interesting here is in thread C we are locking 1, and then we are locking 2, and then we are unlocking 2. So if you think about it, this one is going to be done first. Lock number 2 will be locked the least amount of time, and lock number 1, well, first you have to wait to get lock number 2, and while lock number 2 is locked, you wait for lock number 2. So while lock number 1 is locked, you wait for lock number 2. And what ends up happening is lock 1 stays locked for a really long time. And thread A here uses lock 1. So what ends up happening is thread A never really gets a chance because lock 1 is always locked almost. And so that is called thread starvation. Now, you'll never literally starve a thread, right? It will never run 0% of the time. If you run your thingy for long enough, it'll usually get a few runs in, but it will give a suspiciously low number of runs. So let's see what happens if we change this around. Let's say we now get lock 2 in the spotlights here, and I'm just gonna change the delay to 5 because I think you guys get the point. Let's see. And in this case, the statistics are almost swapped, right? Thread B is starved because thread B relies on lock number 2, and now lock number 2 is almost always locked. It's the longest locked lock of them all. So this is not only an example of resource starvation, but it's also an example of something that we call resource contention or lock contention. Lock and resource, they are kind of used synonymously in most concurrency talks and articles and stuff like that. And so contention means that we have 3 threads all fighting to get a lock, right? They all want to get a lock in, and that's called contention. And the lock number 2 in this case is very contended. Right, so that was starvation. And now we get on to my favorite part of multithreading, which is conditions. So conditions are a really handy way to model the real world, right? So here I have a little bit of text on the slide. The example is to make pancakes. You wait until the pan is hot and then you add the batter. So waiting until something happens, that is exactly what a condition variable is for. And so a condition in the context of multithreading kind of means a different thing from a condition in the usual sense, right? Usually you say, oh, you have an if condition, but in this case I really mean a multi-threaded condition. So I have a little demo prepared for that as well. I'm gonna take some water, guys. I'm not used to talking for this long. Alright, so here we have our condition variable. So this is what Pthread uses to kind of store some internal stuff, and it requires an all capitals initializer. And in Pthread, which is kind of manual, you have to manually lock your condition variable, because otherwise you get a race condition again. And note the 2 conflicting usages of the word condition in that sentence. Yes, it's kind of confusing. So imagine a kitchen, right? And you have one guy whose only job it is to add batter to frying pans, right? Imagine in a kitchen a guy is standing there with a ladle in one hand and a container of batter in the other. And his only job is, when he's called, he has to add batter to a frying pan. So how we do that here is in the batter adder function. This is going to be the thread that adds batter. We lock the condition lock, and then we have this special function here called pthread condition wait, and it requires pass by reference, or I mean pass by address, and then here we unlock it again. And what this will do in effect is this will block until this condition is finally triggered, right? So the thread will just keep on waiting. It will get stuck on these 3 lines, and only when the condition is signaled from another thread, it will continue execution. It will print apparently it's hot, and then it'll take 2 seconds to add the batter because it's quite a slow guy, and then he finally returns. And so here we have the main process. You can think of this as the chef, and the chef heats the pan, which takes a while, and then he yells the pan is hot, and then he signals the condition, right? And to signal a condition you have to lock it and unlock it. and once he has signaled the condition he tells us that he has, and he waits for the batter adder to finish his job, and once the batter is in the frying pan he'll cook it, and it takes 2 seconds and then the pancake is done. That's a really quick pancake, and we're gonna compile that. We'll call it pancake, and then let's run pancake. So it's heating the pan, and there you go. So what happens here is our main thread here yells the pan is hot, and then signals the condition, and then it prints signals the condition. So that's what happens here. And then this thread springs into action. Apparently the pan is hot, right? It waits 2 seconds, and then control flow is resumed here because we are waiting for the thread to finish, and we say cooking the batter, and the pancake is done. So that's a really simple example usage of a condition variable, and condition variables are really useful. For instance, well, I guess in games you can use this a lot. Keyboard events, input events, that sort of thing. If you've ever programmed in JavaScript, you will have worked with events, and this is how it kind of works behind the scenes, I guess. Another option to handle user input is in a loop. You know, you have an infinite loop, and every iteration you check whether some input key was pressed or not. But that's really inefficient, and a condition variable doesn't waste an infinite loop. It doesn't waste a processor core just spinning on an infinite loop. So those are conditions. Oh yeah, and there is a danger for deadlock here. If there is a mutual dependency, for instance, one thread is signaling the other thread, and the other thread is signaling the one thread, and they're kind of in step lock like that, then what happens if one thread kind of dies and it doesn't really signal anymore, then the other thread will just wait forever, and there will be no more progression, and that is called a deadlock. Alright, now a little bit about atomic. This talk is already pretty long, and I don't want to spend the whole night talking about this, so I'm going to handwave a bunch of stuff. But atomic comes from the Greek prefix a meaning not or un, and the word tomo meaning cuttable. So an atomic thing is something which cannot be divided anymore. It is the smallest imaginable unit, right? And nothing is guaranteed to be one action. We saw earlier in the counting example, we got a really weird number. Instead of, we had 8 threads and they all incremented 10,000, right? And instead of seeing 80,000, we got this really weird 35,000 number. And that's because the plus plus operation wasn't atomic. Now, a plus equals b, that's also not atomic. First you load a into a register, then you load b into a register, and then you sum the two, and then you write the result back into the memory of a. And we have already seen how that can cause a race condition. And atomics kind of help us. They let us pretend that certain operations are a single action, right? They are undividable, and the race condition cannot happen. Now, the kind of actions which are atomic, it's kind of limited, right? For instance, hold on. Oh, right. So all compound assignments are atomic, right? So plus equals, times equals, minus equals, and regular stores, so a regular equals a equals 5, a plus equals 5, those are atomic. And a load is also atomic, so if you say b equals a, and a is an atomic variable, that will happen atomically. And the compiler will kind of insert a lock for you, and it doesn't have to be a mutex. Sometimes the instruction set, kind of your CPU, the lowest level machine code, has a way of dealing with atomics, and the compiler knows that, and it will prefer to use those lower level methods. And now there are 3 ways to declare a variable as atomic in C, and it's kind of ugly, and I don't really have an explanation for it, but my advice is to pick one and stick with it. I like to use the underscore capital A atomic and using that as a separate keyword, but they're all the same thing. So we got in the chat some comments about shoe shooting. Yes, you have a keen eye. So here's an atomic example, right? Here's that counter example again. We have a counter. We have 8 threads. I define num threads to be 8, and we have 8 threads, and they all add 10,000 to the counter, right? They do this 10,000 times. So let's see what happens. And let's call it count. And we'll run the program count. And we get a correct result. We don't get any weird 35,000 sort of weirdness. Now what happens if we strip away the atomic key word? We get a weird number again. So atomic is definitely helping us here. It allows us to kind of remember in previously we had to manually do pthread mutex lock and pthread mutex unlock and all that extra code. It's now gone. So atomics are really useful for making shorter code. But there is one difference, right? Which is this code probably performs worse. Why? Well, we're doing this 10,000 times, and for 10,000 times we are incrementing our counter. And at each increment the CPU locks and then unlocks, right? That's what atomic means. And the whole problem with that is that we now have 10,000 locks and unlocks, whereas if we just manually locked the loop, we would only have one unlock instead of 10,000, right? One lock and one unlock. The obvious example here is to just forgo all of this and do counter plus equals 10,000. Is that 100,000? Yeah, here we go. That's also a valid solution, but keep in mind, sometimes you can't always just swap out a lock for an atomic variable. It might have a little bit of a performance implication. Alright, so now we go to the food shooting guy. Oh wait, actually first I thought it would be interesting to kind of show you what the assembly looks like. So here is x86. If you are using an Intel processor or an AMD processor, you are running this instruction set most likely. And what happens here is above we have C code and below we have the compiler generated assembly, right? And you can see that they are pretty much equal, except on the right hand side we are using an atomic variable. And what happens is x86 has this thing called a lock prefix, right? So instead of a pthread mutex lock, we just have it right in the assembly right there. So I thought that was kind of funny. I added a link here which contains just this code, so you can play around with it after I publish this material. Alright, foot guns. So here's a spin lock. A spin lock is one way to implement a lock, right? So we saw the pthread mutex thingy. It might be implemented like this. I don't know if it actually is, but it could be. And what we are doing here is we have some sort of variable I, and we are waiting for I to not be 1. And so once I equals 0, that means it's unlocked, and then we can lock it ourselves. Now I equals 0, I equals 1, that comparison there, that is atomic. And later on we set it. We say I is equal to 1, and that is also atomic. But in between it's not atomic. Alright, what can happen here is that we have 2 threads which are both spin locking, and both of them enter the loop at the same time when I is unlocked. Both of them see I is unlocked and they're like, oh great, I'm gonna lock it for myself. And now we have 2 threads which have entered the lock. So what you really want to do here is wrap this entire function body in a normal pthread lock. Atomics don't really help you here. Now you can use the atomic instruction here, atomic flag test and set, which is often abbreviated as TAS or TAS. And what that does is, I have it here on the right hand side, it tests if flag is equal to 1. Regardless of that result, it sets it to 1. And then it returns what flag used to be, right? It returns the previous result. And it does that as one single atomic operation, so no data races. And well, here's a correct spinlock implementation using the atomic flag test and set. And note that in the while loop, if it was already locked, well, we just try it again. We keep looping. And once we exit the loop, right, it means that atomic flag test and set return 0. While 0, it breaks, so it continues to flow beyond the while loop. And apparently it was unlocked, and we locked it, and everything's great. Another example, another such instruction which is often used is the compare and swap, which is CAS, and it kind of does the same thing. Now, I want to go back to this bug here. This is called the time of check to time of use bug, right? So there is a little bit of time in between where we check if the lock is locked and where we set the lock to locked, right? We check it, there's a bit of time, and then we use it. So this is a time of check to time of use. This is also called the ABA problem, which is kind of similar. Here the spin lock is thread A. Thread A checks whether I is equal to 1, and then maybe some nefarious thread B swoops in and takes the lock, and then thread A continues again and it sets it to 1, right? So there two threads are kind of scheduled throughout each other, and that is it's called time of check to time of use, or the ABA problem. As far as I know, those are completely synonymous. Alright, we are nearing the end of the talk, and I promised a little bit of a rant about the volatile keyword. Volatile was originally meant for memory mapped input-output. So you have some sort of memory address, and whatever is at that address can change. For instance, from some sort of input event, or maybe you're using it to output. And this happens a lot on embedded devices, for instance, right? You have your memory address, and maybe you have some sort of LCD module set up somewhere, and if you write to I don't know, address number 20, then you're writing to the LCD's memory, right? So that's what volatile is for. So it's meant for things like memory mapped I/O. And there are a couple of guarantees that volatile brings with it, but they are kind of they are orthogonal to multithreading, right? You can use multithreading and volatile, you can combine them, but you don't have to. And if you are multithreading and you want an atomic variable, you just have to say atomic. You can't call it a volatile. Sometimes you see code which seems to treat the volatile as some sort of atomic replacement. It's not. It's absolutely not. And volatile is also used a lot in micro benchmarks, but that's also problematic because, again, it's kind of orthogonal, right? It doesn't really have anything to do with micro benchmarking. It has to do with memory mapped I/O, and well, so that's my advice for you. Don't use volatile unless you are actually working with memory mapped I/O. A little bit of an interesting note here is that the atomic flag test and set function requires a volatile atomic flag. And that is because I guess they wanted to allow for the flag to be memory mapped. I guess. I don't really know what they were thinking. Probably something like that. But yeah, so that's my little rant on volatile. Now, there are some things which I didn't mention, which are kind of essential to concurrent programming. Semaphores are a really big one. Barriers, thread pools, coroutines, blah 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 blah. I implore you to look this stuff up because it will help you become a better programmer. But with the stuff that I mentioned in this talk, you'll probably already be able to solve about 90% of the problems that you might want to solve in a concurrent way. And then for those who are extra interested, I have compiled a little list of further reading. And here's a little fun game about deadlocks. deadlockempire.github.io, which will kind of put you in the shoes of the scheduler, and you can try to crash a program. Alright, so I think that I have to scroll back a bit. I might have missed some questions here. If anybody has questions, I would like to hear them. And if you don't, I will wait until somebody comes forth. Why was somebody shooting his shoe? Alright, so this picture, right? Somebody is shooting his shoe. It's called a foot gun. A foot gun is kind of I don't know. It's a programmer meme when something looks like it should work, but it's really easy to abuse it in a way that it behaves completely unexpectedly. That's called a foot gun. And so I thought it would be funny to add a picture of a foot gun. Alright. Oh, somebody says here, most do not optimize macros, like in Quickbench, are just volatile wrappers. I would say, what is your advice, what to use instead of micro benchmarks then? So, that's a good question. First of all, volatile is like a little bit of TNT, but you can also go nuclear. Let me find a folder here, programming bench.c, I think. Let's see. No, I think this is the wrong one. Because I do have a little trick here. One trick that is often done is to create a little bit of inline assembly and to tell the compiler that that assembly can affect any memory, and it's kind of like a stronger volatile, I guess you could say. Let's see if I can find it real quick. Let's see here. Maybe it's right here. Nope, that's something else. Benchmark. I'm just clicking anything that has the benchmark in the name. Nope, that's not it either. Okay, now I'm getting kind of worried. I don't think it's in here. Let's see here. In C maybe? No, maybe cursed. No. I have no idea. Hold on, actually. We are going to search every program for something that contains the assembly keyword. Ugh, I always get the argument order wrong. Oh god. Let's see. We got a huge word list here. None of this is really what I'm looking for. No, I think I deleted the file. Anyway, there's this C++ talk out there which is all about micro benchmarking. I think if you look it up, C++ micro benchmarking talk, you will find it, and that will contain all of the information you would ever want about micro benchmarking. But in general, I'm kind of against micro benchmarks because they are of limited use. In a micro benchmark, you are stripping away all of the context from a program, and what tends to happen is the compiler can optimize a lot better with the context, and so the function that you are benchmarking ends up not really the function that you actually end up running if you compiled it normally in its normal circumstance. So that's why I don't really like micro benchmarks, though sometimes they can be useful. Right, any more questions here? Can you cast to atomic to do a single operation atomically? I don't know. I can't really answer that with confidence. I would say no, probably not. It's probably best to just start out with an atomic variable. Alright, somebody here says this line of code is the clobber. Let me just copy that. Oops. Right. This is just completely insane syntax, and it tells the compiler, alright, here's a little piece of unknown assembly. It affects all memory. Let's see here. For your information, volatile just makes reads and writes side effects. For everyone who isn't familiar with it. Yeah, exactly. So, volatile, right, a side effect, an unknowable external effect. Another thing about volatile is that a value is never cached. If you have some sort of, let's say you have volatile int pointer p, and p points to a volatile int, then every time we do a equals p, it will reload this value. It will never cache the value of p. So that's also something that volatile does, which you may or may not want in your micro benchmark. Oh yeah, counting nanoseconds, micro benchmarking C++. Yeah, exactly. That seems like the right one I meant. Somebody here says switching between atomic and non-atomic on a single memory location requires ensuring you have no cross-thread borrows. I agree. Alright, so did I miss any questions? I'm gonna wait for I guess a minute or two in case people are still talking or typing out their questions. I don't really think that there are any more questions in the queue. Alright, somebody asks how to get the available cores for my process. That's a good question. I don't really know. This is, it tends to be, I know that Pthread doesn't have something built in for it. It is really operating system platform specific. You really need to look that one up on a site like Stack Overflow or something. Oh, how to get the available threads for my process. Oh wait, you mean like a list of all of the running threads? I suppose you just have to kind of keep track of them yourself in C. Oh, and there's also some activity in the Discord chat. Oh, but no questions. Alright. Somebody says, for your information, warning, and then nothing. Well, that's kind of ominous. Oh, right, so you can have more threads than there are CPU cores, and the operating system will just kind of figure it out, and it will it will schedule them. So if there are more threads than there are cores available, the operating system takes care of it, and it will just run fine. It'll run slow, but it'll be fine. Alright, somebody here says fork returns -1 on failure, and kill -1 kills all processes on your machine. All of the ones which it can kill. Right, that makes sense. Well, since we don't really seem to be getting any more questions. Oh, somebody here says you generally should use the same amount of threads as cores. Right. What I usually do is I have one extra thread, because sometimes the thread will just end up waiting, kind of deactive, right? And if you use one more core, you tend to get a little bit better throughput, but this really depends on your individual program. You have to kind of benchmark it, I guess. If you are doing really I/O heavy work, like every thread is reading and writing from a file, um, that probably won't be really nice, because the operating system will just funnel all of it to your hard drive, which kind of defeats the purpose. And if you are using it to do networking, then you might actually have a benefit if you use more threads than cores, because some of the threads will be waiting to receive. Somebody says, for example, right now I have 4,000 threads running on my system, but I only have 6 cores. How can the OS handle such a big difference in the numbers? Well, it really comes down to scheduling, and the operating system uses some sort of scheduling algorithm. The operating system knows how many threads there are, how many processes there are, and it tries to ensure that every thread and process gets a fair share of CPU time. How exactly it does this, you would have to look at the source code, but if you look up scheduling algorithms, uh, that'll get you an answer. Alright, well, um, I think that it is now time to end this talk. That was pretty fun. Good audience, lots of useful questions. Thank you guys for having me. Oh, I'm gonna wait just a bit longer for this discussion to end. Kind of rude to interrupt. Alright guys, thank you for watching. Yeah, this was pretty fun.